Okay, so our next talk is Morse non-uniform for branch surfaces by Rachael.
So thank you very much for the invitation, and I very much regret not being there with the sun and the ocean. And this is ocean. A little behind me is a little ocean further north, East Coast. So I want to talk about most normal form for branch surfaces. And this is joint work with Charles Delman. And all the Adobe Illustrator pictures are thanks to Charles. And then you'll see a few hand-drawn pictures by me. So you'll see very much why I'm giving a big call out to Charles. So we've heard a reasonable amount of talk about foliations. We're going to be in the setting that M is connected, oriented and compact. And I am going to at some point be lazy and just add in the condition of irreducible. Though, if you have a co-oriented taut foliation, you know for sure that your manifold is irreducible. So, I'm being a little bit sloppy by doing this. F is going to be a co-oriented taut foliation and CTF. And I guess this is the notation. If I was following Steve, I would have lowercase. And if anyone can tell me how to do better transverse intersection when I'm doing these slides, this is my pitchfork. But it means that F meets the boundary transversely. And if you prefer to think in terms of tangent bundles, so, you've got this decomposition, you can think about, we're assuming that the tangent bundle to our foliation is C0. So I'm getting a little bit ahead of myself. So we're going to be interested in codimension 1 co-oriented foliations of our 3-manifold. So we're thinking about taking our 3-manifold and it's decomposed as a union of surfaces so that locally things are nice. Locally, you just see R2 cross, you see little horizontal planes in the sense that you have a foliation atlas and charts are modeled on R3 with the foliations just looking like the leaves just passing through this R3 chart as a Z equals a constant. And we're going to assume co-oriented. So we're just going to think about, when we think about this foliation atlas, there's this consistent choice of partial del Z pointing in the Z direction is going to give us our positive orientation. But we're a co-oriented thing in an oriented 3-manifold. So I'm going to equally well jump between, maybe sometimes I say oriented foliation, maybe I say co-oriented, mean exactly the same thing. So manifold is locally modeled by these R3 in the horizontal planes. And each of these planes pieced together to give these surfaces. And so just to do a warm-up 1 dimension lower, let's suppose we're in a surface and we have a 1-dimensional foliation. Then locally things are really boring. We just have things that look like Z equals a constant. But globally things can get, kind of interesting even in this 1-dimension lower situation. Though, as you get these little charts, they cover your surface. And globally, you just have your surfaces decomposed as a union of maybe there's some circles, maybe there's some non-compact leaves, which are R. And Steve yesterday talked about Rabe annuli. And I think his picture of a Rabe annulus was better than my picture that I have right here. But you should be thinking, okay, we've just got a usual model of my Rabe of S1 cross 0, 1. So we're still in the surface world. We're thinking of an annulus. And then a Rabe annulus is just an annulus together with the foliation that has exactly 2 compact leaves, the circle at the top and the circle at the bottom. And then an S1's worth of copies of R. Whereas if you took one of those copies of R and took its closure, you would see the 2 circle leaves. And 1 dimension higher, you have what's called a Rabe component. So if my picture was a little more symmetric, say, you could think about just rotating it around let's see if it's XY, around the x-axis, and you would generate a solid torus with exactly 1 T2 leaf and then S1's worth of R2 leaves, where if you took the closure of any R2 leaf, you would see the torus boundary of your solid torus. So RAPE component, we're thinking S1 cross D2 with this particular type of foliation. But let's think about going up a dimension now. But let's use the crutch of we understand laminations in a surface. So think about taking your favorite geodesic lamination in a surface. Well, let's think about starting with your manifold. Your manifold is just going to be a fiber bundle. So you take a surface across I, you glue to the top by the bottom, top to the bottom by your homeomorphism phi. And we're considering the case that phi is pseudo-nosov. So there are a pair of laminations, lambda S and lambda U, that get fixed by phi. So we can form this foliation F by just, let's say, consider the stable lamination cross 0, 1 glued by phi. And this doesn't fill up the whole manifold, but we know that the complementary regions just look like cusped disks or cusped punctured disks with one puncture. And so the cusped disks without the puncture, they're just solid tori with cusps. And so in the case that I've got pictured here, where we have a disk with 4 cusps, you can think about adding in these leaves and S1's worth of leaves of the type that we have these saddle leaves. So you should think about, you've got these 2 ends that go off to infinity, these 2 ends that go off to infinity, and they're limiting on the R's cross S1 that you see right there. And those punctures, well, we're really secretly interested in closed hyperbolic 3 manifolds. And so you can think about doing a Dane filling along the torus boundary components of your manifold M, if you have any. And then what are you doing? You're doing a Dane filling along a core of a solid torus. So whatever choice you make, you're going to get a solid torus back. And as long as, I mean, I guess I haven't included in here that we're thinking about I want transversely oriented. So I'm thinking about lambda S itself. We're in a case where that's transversely oriented, and phi glues lambda S to itself in an orientation preserving way. And so then we just have solid tori with cusps, and we can play this sort of monkey saddle, S1's monkey saddle worth of games to fill this lamination to get a foliation of our 3 manifold. And this is a construction that's been known for a long time, dates back to, I think, Thurston, Geese, and others. So F is taut if for each leaf L of F, there's a simple closed curve that passes through L and is everywhere topologically transverse to F. And equivalently, there are no dead end components. So there isn't a collection of torus leaves. I remember the torus leaves are oriented because my foliation is. And there isn't a collection, a homologically trivial collection of oriented leaves. So they don't co-bound an oriented submanifold of your manifold. So F is taut, though. We can think about it. We've got, for every leaf, there's a transversal that passes through that leaf. And that's equivalent to there's a transversal that passes through every leaf of the foliation. And in particular, the sort of easiest example of a dead end component is a RAPE component. So if you're taut, you have no RAPE components. So you can think about a codimension 1 foliation gives you this globally defined notion of horizontal motion. So you can move through leaves, we consider that to be horizontal. You can move transverse to leaves, we consider that to be vertical. And so you can think about the foliation gives you locally these little, Morse functions. You have locally a little notion of height. And tautness means that you can get anywhere in your manifold by vertical motion. So you have locally a little local circle valued Morse function. And this is why these foliations are helpful. or one of the reasons. So you could think about, well, here's a first little theorem. It's just that every manifold contains a core-oriented foliation, and there are lots of three manifold constructions, and then there's Thurston, we're in an Euler characteristic M0 manifold. But this most theory type games allow you to conclude at least the beginnings type things. You can show that, if you have an S2 sitting inside your manifold and it has a core-oriented taut foliation, really you just need Rabless. You can think about putting that sphere in general position with respect to the foliation. And then you can play standard games to show that, well, the only way in which you can see an S2 is if you're an S1, if you're an oriented three manifold, is if you're an S1 plus S2. And so M irreducible is a conclusion you can get. You can also think about, these transversals to the foliation give you infinite order elements in the fundamental group. So Novikov tells us the fundamental group is infinite. Palmyra showed us that the universal covers all three. Thurston, again, playing these general position games, showed that if you have a compact leaf of a taut foliation, then the surface is minimal genus in its homology. Okay. Eliasberg Thurston proved that there's a pair of contact structures which are weakly symplectically fillable in universals. And they proved this with the condition that the foliation is C2. So the foliation atlas can be chosen to be C2. And then independently, Bowden and Gazez and I showed that you could throw away that constraint. So you need to have the tangent plane field nice enough, so C0, but as long as you do, you're fine. And so Ashwath and Szabo then use this to show that if you have a co-oriented taut foliation, you can use contact structures to show that you're not in L space. And Tao Li told us about this yesterday. So in particular, M is an L space if it is the simplest possible in the Hegod floor sense. So if M is a rational homology sphere and the rank of HF hat is equal to the cardinality of the integer first homology. So having a foliation gives us information, and it gives us, in particular, gives us this nice local picture and this nice way of traveling through our manifold that we can hope to make use of. So a brief survey of existence of CTF. So remember, if you have a CTF, you're irreducible. So from now on, I definitely am assuming that my manifold is irreducible. So if M is not a rational homology sphere, then Gabai tells us that M contains a CTF. And we heard quite a lot of details about that thanks to Ian. And there are lots of CTF examples. And I look at this list and I realize there's this horrible danger of listing names when there exist many. And I can see already that I've left out Kal-El-Kar, and I've also left out, I should add in Boyer, Gordon, and Hu. And please let me know if you notice any others that I've missed. But there are sort of many settings in which one can construct things, but there's no really nice global thing once you're in the hyperbolic world. If you're not in the hyperbolic world, if you're geometric but not hyperbolic, then we have the L-space conjecture satisfied thanks to Eisenbud, Hirsch, Neumann, Jenkins, Neumann, Naimi, Liskus, Dipschitz, Boyer, Roffs, and Wiest, and Boyer, Gordon, and Watson. And if M is a Groff manifold, again, thanks to Rasmussen, Hanselman, Rasmussen squared, Watson, and Boyer, Clay. Yesterday, we heard from Tao Li. So Sarah Rasmussen proved a weaker version of this. And then Tao Li gave a really nice proof that we saw yesterday that left orderable implies that there's a co-oriented taut foliation in the case that your manifold is Hegod genus 2. And so we have this conjecture, which again has been spoken about already, that again, you're thinking about rational homology sphere, you're thinking about irreducible, that NLS is equivalent to CTF is equivalent to LO. So somehow analytic, topological, and algebraic information are all telling you the same things. So thanks to this L-space conjecture, interest in taut foliations was revived. But there's also underlying the question about, can we classify up to some equivalence all taut foliations in a given M? Suppose we get greedier. We don't just want to show there exists a taut foliation. We want to understand not just when they exist, but how many there are. And we need that up to some equivalence, because if you think about doing a small perturbation of the tangent plane field of F to the tangent plane field of another foliation, where these tangent bundles are close, typically you're going to get non-isotopic foliations. So when you think about this classification problem, you definitely want to choose an appropriate notion of equivalence. And there are many possible choices. Okay, so one problem when you're working to find foliations is figuring out somewhere to start. So I throw you a manifold and I say, does it contain a taut foliation? That seems to be a much more difficult problem than, well, we know it's a much more difficult problem. So I would have to modify this in a way. But if I throw you a manifold with boundary, well, for example, we have Gabai's result, and we know that there are CTFs, and you can sort of grab hold of the boundary and use that to generate foliations. So one of the games you can think about is to say, well, any manifold, and maybe let's restrict attention to hyperbolic now. Any hyperbolic manifold can be obtained by doing Dane surgery on knots, on links, various types of things. And so you might say, oh, okay, well, let's see if we can succeed everywhere where we might expect to succeed in manifolds that are obtained by removing some knot or link from the manifold we're interested in. And I just wanted to note that we need to be a little careful when we do this. So imagine you have a knot or a link in M, and you think about drilling out a knot. And maybe, for example, you want to drill out a knot so that M minus the knot is something fibered. So you don't have complete choice of that gamma. If gamma is a transversal to F, then we can play this, we can certainly remove a neighborhood of that knot. And we have this foliation in the complement that is still going to be taut, and that meets the knot in parallel circles, parallel meridians, meridian for the Dane filling we're planning to do. So in this case, if I am looking for, if I know I have some foliation in my manifold M, and I take a transversal to that foliation, I'm going to see the foliation with my removed solid torus eyes. I'm going to just see something that meets the boundary transversely in parallel meridians. And if gamma, another possibility is that gamma is tangent to the foliation. So gamma is isotopic to a non-trivial loop in a leaf. And in this case, again, I'm going to be able to see the fact that there existed a foliation in M from the manifold that I've obtained by removing the knot. So there's a observation goes back to Thurston that if you have this setup, then there's going to be a taut foliation that meets the boundary transversely with rave annuli in the boundary. So remember, the boundary is a torus or a union of tori, and foliation is meeting the, you've got this loop that just isotopes to lie in some leaf. And then you can play games to show that you must have one of these taut foliations in the complement of the knot of the gamma. But if you just think about drilling out some arbitrary knot, you can insist that it be piecewise vertical and horizontal. So it lies alternately horizontally and then vertically. So it can be subdivided into little segments that lie in a leaf, transverse to a leaf, in a leaf, transverse to a leaf. You can insist that you've got, smallest such subdivision or concatenation. But in this case, you might not see the foliation from M minus the neighborhood of gamma. So in this game, it could be that we happily start with some manifold that has a foliation. We drill out a knot to get some manifold with boundary that's nice in whatever way niceness means to us. But we've lost sight now of the foliation. And yes, there's another knot we could have chosen, but it begins to be subtle. Okay, so just something to keep in mind as a caution. Now let's think about going in the reverse direction. So we start with X. X is a manifold with torus boundary, and it has some foliation. And we're asking, well, can we extend this foliation over the Dane-filled manifold? So we're in the opposite world to Steve yesterday. We're thinking about the tori just bound solid tori. So X hat is a Dane-filled X. TF is, F is a co-oriented taut foliation transverse to the component that we're filling. And we're saying, well, how do we construct an F in the Dane-filled manifold? And if we have a union of circles, then we can just cap off the circles to get foliations in X hat of M. And I think Ian might have been the first person who talked about doing such things. If we see Rabe annuli, so for example, if we had a leaf, if we think about starting with our previous story where we had M and we had some gamma that was isotopic into a leaf, we can modify our foliation so that it's still taut, but it meets the boundary in Rabe annuli with cores of some slope. So I'm just thinking I've got a Rabe annulus. That means I've got circles bounding my Rabe annulus, and those circles have some slope, or the cores of the Rabe annul have some slope A. So Gabby tells us that if you're doing a Dane filling on any slope that's not equal to the slope of the core of the Rabe annuli, then you can extend the foliation into the Dane-filled manifold. So in a sense, we're used to, or at least I'm used to thinking about Rabe components as being bad and Rabe annuli as being, the one dimension lower bad. But in a certain sense, they give you a setting in which things work much more easily. And then we're in a situation where we get stuck unless there's some way to modify what we were starting with. If F is transverse to the boundary but has non-trivial holonomy but no Rabe annuli, then F doesn't necessarily extend. And we need to work harder if the goal is to show existence. So Steve talked about non-trivial holonomy. My boundary is a torus, so I can think about getting that as an annulus with boundary of annulus glued to boundary annulus. And so you can think about just taking the foliation of your annulus by segments. So we have, interval cross S1. So we just take for each S1 a horizontal segment. They get glued by whatever our gluing map is. And the resulting foliation of the torus is called a suspension lamination. And non-trivial holonomy means that we don't just have circles. If I look at, we're in the case where we're wanting to think about a Dane filling, and we're going to want to do a Dane filling if we can only do this if we have Rabe annuli or just circles. Okay, so we have this problem where we're getting greedy and we're saying, okay, we want to classify co-oriented taut foliations in the manifold, with maybe the hope that if you make the problem harder, it might become more tractable, though in this case, I have my doubts. So we've already noticed that even questions on, about existence seem to be difficult. And there's very, very little known about classification. And so there are lots and lots of open problems. And we would like to find guides to structured searches for new constructions. You know, things that allow us to just dive into the manifold and start looking for these things. And one approach would be to look at the classification of I1 injective surfaces problem. And one approach when the manifold is small enough that was useful is Morse theory. And early work in this direction is thanks to Hatcher Thurston, Floyd Hatcher, and Kala Jacob Rubinstein. And moving on to CTFs, CTFs have been discovered using Morse theory. There's original work of Hatcher and Delman from way back, and well, somewhat more recent work of myself with Charles. And the particular world I want to think about today is thinking about Dane fillings on Montesinos knots. But I want to use this more as a context for thinking about foliations and branch surfaces in Morse normal form. So suppose now we restrict attention, we've got M is obtained by Dane surgery along a Montesinos knot. And then thanks to Lidman Moore and Baker Moore, we know that a Montesinos knot is an L-space knot, if and only if it's a 2, 2n+1 torus knot, or -2, 3, 2n+1 pretzel knot. And thanks to, and so a long time ago, Delman got a lot of results about Montesinos knots, taking in the context of essential. And
hasta allá son como 20 kilómetros.
Es como ir al como Rosedal, ¿no?
And Ying-Ching Wu took these things further. And then thanks to the L-space conjecture, suddenly there was an interest in, well, back in the 80s and 90s, or back in the 90s, the interest was in finding laminations which weren't just secretly foliations, because of wanting to get hyperbolic. And then Perelman came along and said that became not so interesting, but Flow came along and then taut foliations became interesting. So various constructions that existed for essential laminations, one could revisit and think about in the context of taut foliations. And thanks to a question of Cameron Gordon, I started thinking about this small little world where we were thinking about pretzels knots, the sort of remaining pretzel knots, realized Charles was the person to go to. And my contribution here is fairly minor. This is really Charles, with also contribution of Ying-Ching. And then I just wanted to give a shout out to my grad student at Simba, who is working on related type constructions. Okay, so let's get back to some general theory before going back to the Montesinos knots. So a branch surface is just a, and we're going to be thinking about our branch surfaces as embedded in our 3 manifold. And we might as well put a smooth structure on our 3 manifold and choose these branch surfaces to be smoothly embedded, just to rid ourselves of any unnecessary weirdness and to allow ourselves to do Morse theory. So a branch surface is just a surface, it's just a sub-object in your 3 manifold, so that any point has one of these 3 possible local neighborhoods. Either it's got a surface neighborhood, or it lies along the double curve locus, branching locus of my branch surface. So let's see if I can Sorry, I'm scrolling through using my iPad because I wanted to write on it every so often. So we could have a point that lies right here, or we could have a point that lies where 3 planes come together. So we have regular points, double points, triple points, and the union of the double points and the triple points gives us what we call the branching locus. Okay, so we can think about a foliation as being carried by a branch surface. And we can think about maybe Tally's description yesterday. So we have a foliation. We can think about a foliation being carried by a branch surface if, well, there's some issue. You might have to split open some leaves just to create some space, create some eye bundle. But after you've done this, you can isotope the leaves of the foliation so that they lie in a regular eye-fibered neighborhood of the branch surface. And Gabay has a result which says that there are finitely many branch surfaces, so that any co-oriented taut foliation is fully carried by one of these branch surfaces. So you're replacing this world where leaves are typically non-compact with this compact world, which allows you to, get a rough picture of what the leaves look like. Okay, so now let's think about doing Morse theory. And so we all know if we have smooth manifolds and we have a smooth function between the manifolds, we can look at its differential. And we have this notion of critical point. So it's a critical point if the differential at a point is not. So P is a critical point if the differential at that point is not surjective. And so if we're thinking about our N as being the reals of the circle, then this is of course going to occur when our differential just is 0. And any point of N that is not a critical value is a regular value. And we know that if we look at a regular value and we take its pullback, we're going to see a codimension 1 manifold in this case. And we want to say, oh, okay, well, let's think about playing the same game for branch surfaces. So we're thinking about our branch surface as smoothly embedded. So we have a smooth tangent plane field. And so we have a notion of smooth function from a branch surface to R or to S1. And the notion of differential extends to this branch surface picture and the tangent plane fields. And we want to say, well, let's think about choosing nice functions. And again, we could replace all with S1 if we wanted. So let's think about this function that goes from a branch surface to R. And we're going to think about making the following definition that we're Morse normal form if the critical points of F are isolated saddles and extrema disjoint from the branch locus. So let's just scroll down. This is just the usual picture where we can think about, we might have local max, local min, or saddle point. But we also want to impose a condition on the critical points of F when we restrict F to the branch curves. And we want to insist that for each branch curve, the critical points are isolated extrema. So you only see extrema in the disjoint from the triple points. So we've got F, which goes from B. We've got F restricted from to gamma, which goes from a branch curve to R. So let me show what we're thinking about with these branch curves. So for example, we might see something like this, where we've got, if you think about the slices, the horizontal slices, and if we start from the bottom, a horizontal slice will just be a train track with a diagon. And as we move up, that diagon is getting smaller and smaller until at the top, we just see a line. So we can think about this as an example of a little piece of a branch curve. And we see a local max on the left, and we see a local min on the right. So that's one possibility. So remember, we're thinking branch surface, so we have these branch curves. And I'm going to jump down again. Just look at the right-hand side picture here for a moment. I could also see local maxes and local mins in my branch curves arising from branch surfaces of the form that I see on the top right. So we can think about, as we move again, let's move from the bottom up. We see, look below at the horizontal train track we see is the one, let's say at the one on the bottom. And then as we move up, we see that this is the train track slice is changing. But what we have are local maxes, local mins. And this is the only, these are the two models of extrema when we think about F restricted to the boundary, to the branch curves. So for each branch curve, you've got these critical points that are isolated extrema disjoint from the triple points. And we can play the usual Morse game. We can say, oh, okay, well, let's look at pre-images and get these horizontal slices of the thing I want to understand. And then we've got a movie of the thing that we want to understand. And so we're immediately interested in, well, you know, what causes, so level sets now in regular levels are going to be train tracks instead of just one manifolds. And well, it's going to change in the usual way. The level set will change as we move through a critical point of F, because those just correspond to isolated saddles and extrema. And we could also have an extremum of a branch curve. And we saw a few minutes ago that we can, things change. Corresponds to a splitting or pinching of a train track as we move through an extremum of a branch curve. And if you cheated and looked at the picture to the left of the branch locus picture, you saw how triple points also correspond to splittings of train tracks. So let's just jump down. So here is just standard critical points of here we have the first type of extrema of the branch curve, splitting of a train track as we pass through one of those things. So I can think of those as birth and death of digons in the level train track. And we can think about, let's see, so we've looked at the type 2 extrema of a branch curve. So if we look at the left, let's think about passing through a triple point, which doesn't correspond, we know it doesn't correspond to an extremum of F restricted to the branches. And so what we see are those two possibilities on the left. So we can think about our triple point is lying on what looks like a vertical X in the picture on the top. And then we can note that as we move either up or down, what we're seeing are the train tracks varying in this way that corresponds to splitting. So you can think about, forget the name non-geogenic vertices. So it's just, this is a picture stolen from a paper, splittings of the level train track. Okay, so we've got this notion of Morse normal form. And if I give you a branch surface in my 3-manifold, and I've somehow got some natural height function, I can think about isotoping the branch surface to be in my Morse normal form. And so I'm going to show you some pictures of that sort of game in a few minutes, but I think it's useful if you haven't thought about these pictures to go back to Hatcher-Thurston, 1979. So, which is before most of you were born. So let's think about this picture. And let me jump ahead with thinking about just the usual Seifert surface of the figure 8 knot, say. So let's think about drawing my figure 8 knot in the way that I've drawn here. And we're thinking about the Seifert surface we get, the minimal genus Seifert surface we get by just plumbing two bands, one with left-handed twists and one with right-handed twists. So we know what this surface looks like, but think about describing this surface by describing its levels. So we can think about, I'm sorry, let's go back up here. So if you look at these two horizontal lines at the top, you can think about taking these two things and saddling them together. And after the saddle, the horizontal slices you'll see are these. Keep moving down. Here we've got two half twists until we get here. And then here we have another saddle. And after this passing through the saddle, these are our level arcs. Again, we can pass down. We've twisted 2 times. We pass down to here. And then we saddle these together and we end up with these 2 arcs right here. So this is the picture that we see here. We started with these 2 arcs at the top. We've saddled. You end up with 2 arcs here. Twist one side twice. We then saddle again. And we get these 2 arcs, twist twice again, we get to here, and then finally we've got those arcs right at the end. And you can also equally well picture this without doing the 2 half twists. So if we think about doing the saddle, we end up with the 2 arcs as before. But if we think about look at this picture and undo the twists, we end up with the saddle looking like this. And again, undo the twists, this saddle becomes this one. And at the end, you have slope 2/5. So if you're used to thinking about 2 bridge knots, you can think about, oh, okay, you have these 2 bridges, and then you've got those 2 slope 2/5 arcs right at the bottom. But just 2 different, most normal ways of describing the Seifert surface. And Hatcher-Thurston evaluated, you start with this 2 bridge knot, and you think about getting some sort of controllable construction that allows you to see all pi1 injective surfaces. And they introduced the notion of the path and ferry diagram, and this really beautiful picture classifying all the pi1 injective surfaces in the 2 bridge knot complements. Okay, so now let's think about, again, let's begin with the same example. So we're thinking about a figure 8 knot complement, and we want to say, oh, okay, well, suppose I have the freedom, instead of horizontal slices looking like 1 manifold. So in the case we were just looking like probably embedded arcs, we want to think about the pre-image of slices or train tracks. Or equivalently, if we look at this picture right here, we could say, well, what does this train track carry? Well, I've got a circle about, so this is just where the knot passes through your horizontal plane. And you've got these circles around the punctures. And then you've got this arc, which now is an arc that spirals around the circle, And in fact, you don't just have an arc, you can think about having canter cross section. And now let's think of, instead of having a constraint, so when you saddle, you've got finitely many being saddled to finitely many. And so, well, there's only one homeomorphism from 1 to n maps to 1 to n, where you now have many, many, many choices, infinitely many choices of homeomorphism. And so in particular, you can play games like this. You could think about, well, this isn't really just one arc. This is representing a canter set of things. And you can split your train track to carry the same thing, to look like this. And then do the saddling that's indicated. And if you think about what you get, you're going to end up with, well, there's going to be introduced an arc here. We're not going to have killed this one. when we saddle all the way through. That's why this piece of arc was continued. But we can saddle, we're going to end up with leaves spiraling onto circles again, spiraling onto circles, spiraling from here onto this circle and spiraling around. And again, we can split the picture so that we see saddles, split the picture so that when we draw this, we're thinking about the saddle as saddling all the way through the leaves. So you've got this sort of infinite number of parallel saddles that are happening. And you can keep going, and you're going to get sort of parallel copies of things. Like if you look at the arc that you get starting here, traveling around here, that's going to introduce a digon. So if you see a horizontal digon, typically just pinch it together. So this picture isn't showing every change in what's going on. So we're not seeing these, remember when we were looking at these local mins or local maxes of the branch curve, we were thinking about, we had birth and death of digons. So but in these pictures are buried births and deaths of digons. So when you're translating this to think about what's happening in your lamination as you move down, that's secretly encoded or not so secretly encoded in these pictures right here. Okay, so this, if you look at this picture, and let's think again about what's happening. So we're starting with this figure-8 knot. And if we look at the top, so remember we have the top of our figure-8 knot. We're just saying that we want to start with a foliation where instead of just seeing arcs that run from here to here, all the way up, there's a tube that is running along the knot. And the arc is, instead of just being a properly embedded arc, is a copy of R that spirals around the torus and spirals around the torus. And then really though, if you look at some of the game that's happening, we're playing a somewhat similar game to here. It's just that you've got many more choices and a lot more freedom in what can happen. Now, if we construct something where we always have a little circle running along the knot, that's going to be really bad. We're going to have a boundary parallel torus, and certainly that's not going to behave well along Dane fillings. But if you notice what's happening here, there's something mysterious happening to this circle we had here because we're saddling all the way through this one. And similarly, this circle right here, we're saddling all the way through this one. So if you move over to see what you get, there's now not a little circle wrapping around here. You have to think for quite, well, most people, or at least I would have, I had to think quite a while to understand what was going on here. But what's going on is the following. There's a creation of a meridian cusp each time that thing happens. And please ignore these lines, they're there by mistake. Well, this one is okay. So we're thinking about somehow, as we pass through that, that game where we saddled and saddled, each time we see this picture, we're introducing a meridional cusp. So right here is a meridional cusp, right here is a meridional cusp. So there were 2 meridional cusps introduced. And so you think, okay, somehow there's this level normal form picture. And I look at this picture and I say, oh, okay, great, this is a meridional cusp. Where do I see it in the previous picture? Well, remember the previous picture was capturing things in most normal form. So if you're thinking about your branch locus, your height function with respect to any branch curve is in most normal form. So you see extreme, you're not going to see a horizontal circle. So this meridian cusp, it's just that in the most normal picture, it's not pictured, in this, it's pictured more like this toilet bowl picture of what's going on. So you can think about this dark tube is just the knot passing through. This red is one of these meridian cusps, and the rest is just the corresponding branch surface that you see. And here's an alternate viewpoint. As you pass through the levels, you started with circle with stuff spiraling, circle with stuff spiraling. And then there's this new, this is where you get this cusp. And here's the other cusp, if you go back to the horizontal slice pictures. And what's nice is if you, so you can think about, you've got this complementary region around the knot, which is a torus with two cusps. So if you think about doing Dane filling, you're exactly that picture we had right at the beginning of the talk. You have a solid torus, you're doing Dane filling along the core of the solid torus. So you're going to get a solid torus back. And that the Dane filling curves are going to have to cross these cusp things an even number of times. And that tells you can play the stacked chair game to get foliations, realizing the filling slope. And let's see, I think these are kind of painful to look at if you haven't thought about them very much, but just to give an idea, here's another picture of this meridional cusp formation, where you saddle through the circle, and then you saddle again, and you get a new picture. And these vertical lines are just saying, oh, actually, I can choose these to spiral, in whichever way. So you can think about freedom of canter cross section. And here's another configuration that's quite useful. And that's that, again, if you're thinking about these Morse normal pictures, having canter cross section instead of finite cross section gives you sort of, there's a lot of things that can happen. And in particular, this thing is supposed to be illustrating that we start with the spiraling going around in the counterclockwise direction, and we end up with spiraling going in the clockwise direction. And that's a useful part of what's going on also. And you can get a little more freedom by allowing half channels. So constructions in which, as you pass through some number of heights, you just introduce a single meridian. And then you do whatever. It just means that somewhere else you have to have introduced another meridian by playing this game again. And again, I should probably bring this to a close. But these are the sorts of pictures you can get. And I think that these can be very useful in certain settings in saying, oh, okay, I don't want to, it's tricky to maybe play some variant of the get-by game, even if you allow yourself to work with essential non-orientable surfaces. But you need some way to begin. And so if you can find yourself a Morse function, you've got a lot more freedom in terms of what you can choose to do when you're looking at the horizontal slices. And so thank you very much. I was thinking maybe the room had emptied out and there was no one left.